Hi, I'm Tina Vodopivec-Seravalli, and I'm part of the pDNA and mRNA process development group. In this video, I will present you the mRNA analytics with our PATfix platform. The recent pandemic significantly accelerated the development of new messenger ribonucleic acid vaccines and other therapeutics. This rapid advancement was driven by the urgent need of effective treatments and preventive measures. Consequently, the in vitro transcription reaction, which produces mRNA, has become the focus of intense research and development. The primary goals are to increase mRNA production, while simultaneously reducing its high cost and minimizing unwanted byproducts. The IVT reaction is relatively complex, involving many different components. The most important among them are capping reagent, nucleotides, pDNA template from which the mRNA will be transcribed, various enzymes, with mRNA polymerase being the most crucial one, and magnesium ions, which we have found to be very important in the IVT reaction. Under the right conditions, mRNA production continues until the nucleotides are consumed. Optimization of IVT depends mainly on understanding the impact of each reagent on the kinetics of mRNA production and the consumption rate of each building block. Low throughput and endpoint-only analytics do not provide the insight needed and therefore can significantly slow down the process optimization. Agarose gel electrophoresis, for example, is a semi-quantitative method that provides limited insight into your sample components. It takes approximately 2 to 3 hours to visualize and evaluate a limited number of samples. Now let's say we are running an IVT reaction, and at the end, we want to determine if we were able to produce any mRNA. After 4 hours of IVT incubation, we inactivate the sample and proceed to perform an agarose gel electrophoresis analysis. At the end of the working day, when the results are ready, we see that our IVT reaction didn't produce any mRNA at all. We evaluate our results and decide to try a different IVT protocol the next day. But even when we do manage to produce and visualize some mRNA, several questions still remain. How do we know if and when all NTPs were consumed? How much of the NTPs remained in the reaction? How can we precisely quantify produced mRNA? The need for an at-line method for IVT monitoring and mRNA quantification was higher than ever. In response, we developed a chromatographic method using our CMAC'-S column. Today, this method is one of 3 validated methods for mRNA production and purification monitoring available in our PATfix mRNA platform. Let's dive into the world of ''S analytics and IVT monitoring. First, let's talk about the column itself. Like our other analytical columns, CMAC'-S is packed in a stainless steel casing, allowing it to withstand higher pressures. ''S is a multimodal chromatography ligand that combines element of hydrogen bonding with anion exchange chromatography. The method we developed and validated has a 4.5-minute readout and is based on the separation of nucleotides in an ascending salt gradient and the elution of mRNA under high conductivity and pH conditions. With our method, we are able to separate capping reagent, nucleotides, DNA linear template, and of course different modalities of RNA. CTP and UTP do coelute. Most of the time, this does not cause a problem, as ATP or GTP are usually the limiting nucleotide in an mRNA sequence. For when it does matter, we offer a mathematical formula that helps track the individual concentration of UTP and CTP using their different extinction factors and absorbance ratio at UV260 and UV280. When performing an optimization of any kind, it is important to have an inside look at the reaction itself. For IVT reaction optimization, the most important part is understanding the kinetics of the reaction. Key factors include: how quickly are the nucleotides being depleted? the rate at which mRNA is being produced, and transcription factor, which shows the mRNA concentration relative to the linear DNA template concentration used in the IVT reaction. PATfix analytics using CMAC'(S) column can answer all of these questions. To prepare for IVT monitoring analysis with PATfix, first we need to connect the buffers and the column to the system. After flushing the system with buffers, we run at least 3 blanks to ensure that the baseline is stable. Next, we inject the system suitability test sample to check the column conditions. If the separation of all components is within expected parameters, we can proceed to the injection of the calibration curve made from our provided mFix4 standard, and after that, our samples. When optimizing an IVT protocol, we sample the reaction over time, usually every 15 to 30 minutes, depending on the protocol we are using and the results we are expecting. We take 2 microliters of the IVT reaction and inactivate it with 2 microliters of EDTA. This binds the magnesium ions, making them unavailable to the RNA polymerase and effectively stopping the reaction. Before PATfix analysis, the sample must be additionally diluted 100 to 400 times with mobile phase A. The dilution is determined based on the predicted end mRNA concentration in the IVT reaction. For precise calculation, you can use the formula from our paper, or, to simplify, the end mRNA concentration in milligram per milliliter corresponds to the starting concentration in millimoles of the most frequent NTP in the mRNA sequence. For example, if we add 5 millimoles of ATP to the IVT, we can expect 5 milligrams per milliliter of mRNA if the ATP is the limiting nucleotide. After the samples are analyzed, we can easily visualize the chromatograms in the PATfix software. When analyzing the data, first we create the calibration curve and apply the calibration to our analysis. After we integrate a sample, its concentration is displayed. After evaluating all results, we can determine the optimal conditions for the IVT reaction depending on our specific goals, whether we aim to produce mRNA more quickly or reduce the cost of the IVT process. The data will guide our optimization efforts. In this experiment, for example, we aimed to determine the importance of the concentration of magnesium ions in an IVT reaction. We designed an experiment where each IVT had a different magnesium chloride concentration. If we only looked at the final points, we might falsely conclude that we only had 2 different outcomes. 2 reactions performed poorly, while all the rest had the same final mRNA concentration. However, by examining the reaction kinetics, we can clearly see that some reactions produced mRNA faster than the others and were completed in under 1 hour. This allows us to choose whether we want the reaction to finish faster, using higher reagent concentrations, or to lower the cost of the IVT by allowing the reaction to run for a longer time. Choosing which one to optimize often depends on our available resources and overall stability of the mRNA at higher temperatures. If needed, we can also monitor the course of the IVT reaction in real time. This is especially important when planning to fit additional nucleotides into the reaction. By monitoring the remaining nucleotide level, we can decide how much of each nucleotide to add to prolong mRNA production and achieve better yields from the IVT reaction. Additionally, when trying new protocols, buffers, or reagents, we can act quickly if we notice that the reaction is not producing any mRNA. By monitoring the reaction in real time, we can attempt to correct the IVT by adding specific reagents, thereby gaining a better understanding of the process and potentially salvaging the IVT. For example, in this reaction, we were testing a new commercially bought buffer. The reaction was not proceeding as expected. After 3 hours of incubation, with little to no mRNA production, we decided to add some magnesium to the IVT. Already at the next time point, we observed mRNA production, confirming that our hypothesis was correct, and the reaction just needed more magnesium. In mRNA production, the most expensive step is the IVT reaction due to the high cost of capping reagents and enzymes. Optimizing this step to achieve higher yields is crucial for reducing overall costs and minimizing process impurities. The PATfix mRNA platform with IVT monitoring method allows you to separate all main IVT components and track them over time to determine the reaction kinetics. You can also use the same method to monitor optimization of mRNA purification steps, where you can identify potential residual impurities and calculate the recovery of each step. To learn more about the PATfix mRNA platform and other methods for mRNA analysis and quality control, visit our webpage where you can try our PATfix demo software or contact our sales team with specific questions.